Okay. Propositions and connectives. We considered the compound proposition. If Mary and Michael are not both left-handed, then either Mary is not left-handed or Michael is not left-handed. This proposition is built up from the atomic propositions. Right? Those atomic propositions are Mary is left-handed and Michael is left-handed. Then you put them together by using these connectives. Okay. We use these 5 connectives. These are the only 5 connectives that we're going to use. Except later we will put some complements as well and we will deal with separately. But anyway, for the time being, we use these connectives. If then is also known as implies. If and only if is also known as is equivalent to. Oh, I forgot to record it. Let me actually start recording. Right. Okay. This is what we did in the last lecture. So these are the 5 connectives that we use. So this is if then. This is also known as implies. If and only if is also known as is equivalent to or same. Right. So notation in propositional logic, we will use lowercase letters P, Q, R to denote propositions. Apart from not connective, this one, the connectives are written between the proposition they connect. What that means, we have done Mary and Michael example, so P and Q and all that. Not is placed before the proposition to which it applies, so that is before. And now, so if P denotes the proposition cows are animals, and Q denotes the proposition cows produce milk, then P and Q denotes the proposition cows are animals and cows produce milk. Okay. This may also be restated as cows are animals and produce milk. The same proposition. You can skip this cow again word, cows again. So you can simply say cows are animals and produce milk. This is what P and Q stands for. So that entire sentence can be squeezed into just this symbol. Not P means cows are not animals. So if you put not before that, this would read as cows are not animals. We are not going into their truth value or whether it makes sense or not. We're just looking at what this would imply, this statement reads. Just the usage of not sign. So remember, not is a unary operator as it applies to a single proposition. It does not connect two propositions together. That's what it means. The other connectives are all binary operators. Now we look at these connectives one by one. So let's start with connective AND. A formal definition of AND follows by stating the truth value of P and Q for each possible combination of truth values of P and Q. Okay, what that means? The everyday understanding of the term AND is that for P and Q to be true, both P and Q must be true. Right? You can give an example, give lots of examples. You want to say that if something happens and another thing happens and you put AND sentence between, that can only be valid if both the conditions hold. For example, if you're discrete math students, then you have to, no, I put then there, I have not put AND. Okay, let me say what example I can have of AND. For example, let's say, yeah, we have a discrete math class. If it's Tuesday and it is 12 o'clock. So you have a discrete math class on Tuesday. Yeah, sure, you have it. But what time? 12 o'clock. If it's not 12 o'clock, for instance, okay, let's say Monday. Yeah. So because on Tuesday we have two classes. So you discrete math class and it's 9 a.m. Okay. Then if both of these conditions hold, then you have a class. So it's like two. Look, there are lots of examples here. Let's look at them. It is Friday and I'm happy. I'm normally happy on Friday. I don't have any teaching, so I'm just joking. No, Friday is the last day of the week, so normally people are happy. They finish work and all that. It is Friday and I am happy. So this proposition is only true if both the components are true. What are the parts? Both the parts. It is Friday. That statement can only be true if it is Friday and you are happy. In all other scenarios, it is not true. Okay. For example, if it is Thursday and you are happy, it doesn't matter, right? That proposition has nothing to do with this. That has to be false. This everyday understanding leads to formal definition of and is presented in this truth table. Look, if proposition P is true, Q is true, then if you put and between, that it is true. Okay? Put that into this example context. It is Friday and I am happy. That can only happen if it is Friday and you are happy. So if both of them are true, then it is true. In all other scenarios, it is false. You can see it's Friday and you are not happy, so it has to be false. It is not Friday, any other day, even if you are happy, it doesn't matter, right? The statement is false. It's neither Friday nor you are happy, of course, statement is false. This is the definition of and it is the same as in daily life. However, if you put or there, then the situation would be slightly different. And what happens in statement or, in everyday language, or has two meanings. Tom will pass or fail. Of course, one of them would be true. It means Tom's result will be either pass or fail, but not both. It can never happen. You flip a coin, either it is head or tail. You cannot ever have both. Right? So, or has, at the moment we are considering only one of the outcomes is true. Sometimes it's possible that both outcomes are possible at the same time. In that case, we call it slightly differently and we will not handle those cases. For example, here we use this or as exclusively. So the possibility of both outcomes is excluded. Okay? Outcomes either pass or fail, nothing in between. So both outcomes, we exclude them, we don't consider them. Tom is smart or studies hard. Both are possible. Okay? Tom is smart or studies hard. Both outcomes are possible. Right? This kind of or connected is called inclusive. That has both the possibilities. But we will not be using inclusive option. We will just use the exclusiveness. That is one of the outcomes true. Okay. So in logic, or is inclusive. So P or Q means P or Q or both. But we would have exclusive as well. Sorry. We would stick with exclusive definition. However, if you want to, inclusive definition, if you want to include exclusiveness, you can do that as well. So what that means is, if I have true and I'm connecting with true, then it's a true value. Both are possible. That's what I meant. So here is the truth value. Tom is smart or studies hard. Both are possible. Or let's say either it is Friday or I am happy. These are medicine doctors writing, so don't worry about it. Just trust the way I'm speaking. So either it is Friday or I'm happy. So one or both the outcomes are true. So if it is Friday, don't look any further. If it's Friday, it doesn't matter what the other outcome is. So the NAND result will be true. If it is Friday, it doesn't matter whatever, whether you're happy or not, even if you're not happy. But since there is an or between, so you get true statement. However, if it's not Friday, but you're happy, since one of them is true, just like the cat and dog and horse example that we did at the start of the lecture today, even then it is true. However, if both the statements are false, then or would give you a false answer. Right. So we have just said that in logic, or is included as the inclusive. Or, so P or Q means P or Q or both. However, there is another connective XOR which we will not be using. That gives you only exclusiveness. That is the same in probability that when you flip a coin, there's only one possibility, either it's head or tail. There's nothing between. Okay. In very, very rare cases, if you flip a coin, it is possible that it lands vertically. That's it. But oh, come on, it never happens. Hardly ever. So we exclude that. All right, so we are excluding exclusiveness. It's just for information only, nothing to do with our work. And the truth table for not is straightforward. If P is true, then not P is false. So it's just the opposite of that. Okay. So if you say it's Friday, and if you put not before that, that means it's not Friday. So that is straightforward. So it changes. It just flips it. Now the other connective, if then, that's implication. Right. Suppose P is the proposition Sue attends tutorials, and Q is the proposition Sue will pass discrete maths. So there are two propositions. We want to connect them by if-then. So how you would connect then? What would be the compound proposition? Michael, what's the compound proposition?
The same.
The same, yes. So what's the compound proposition here? We've got two atomic propositions. We want to combine them by this connected if-then.
Forward arrow. So if you still attend tutorials, so you do the arrow and you assume past the street.
So can you say that?
So like P arrow disregard Q.
P Q, how you would read it?
If P then Q.
If P then Q, what that mean in proposition? What would be the compound proposition? If Sue attends tutorials, then she would pass discrete maths.
Yes.
Yes. Okay. So this is precisely the way we want to reverse it. We will be given, if Sue attends tutorials, then she would pass discrete maths. So we have to rewrite it in this form. At the moment what we did was, I gave two atomic propositions and combined them by if-then. We have to go in an opposite way. So then, okay, so this reads as P here, if Sue attends tutorials, so you would start with if and then there. So it connects both the propositions. Then she will pass discrete maths. So if you want to look at its truth table, okay, let's see if we want to make its truth table, what that would be. While I'm doing, let's try to think about it. That's okay. So we have P. What is P? P is Sue attends tutorials. And then we have Q, and P implies Q. I really want you guys to understand this because that's where most of the students get confused. Okay? Now, P stands for Sue attends tutorials. Okay. And Q stands for Sue will pass discrete math. Suppose Sue attends tutorial and she passed. Okay. So this implication is true. Do you agree with that?
Yes.
Good. Now, Sue attends tutorial, but she does not pass the subject. What's the conclusion for this implication here? False. What made you think that? The claim is wrong then. My claim was, if you attend tutorials, then you will pass the subject. You attended tutorials, but you did not pass, so that means I am wrong. Okay? So that's why it's false. You did not attend tutorial.
Yes, that's actually study hard now.
Okay, now look at other possibilities. Now, suppose Sue does not attend tutorial, but she passed the subject. What would be the implication?
False. So you can't force it.
What?
Well, I think you force it because it doesn't test it really because you don't pass it. So that's the thing. It doesn't.
My claim is, listen my claim again. If you attend tutorial, you will pass. That's my claim.
Yeah,
Okay?
but it doesn't specify if you don't attend tutorials that you will.
So that means my claim is still true.
Yeah.
I did not make any wrong claim. Right? Irrespective of what my, what's the conclusion here? By saying F here, which is nullifying whatever the outcome is. That means my claim stands. My claim was, if you attend tutorial, then something happens. You have not attended tutorial, so that has nothing to do with my claim. My claim still stands. If you have not attended tutorial, my claim has nothing to do. My claim has only to do that if you have attended tutorial. So my claim can only be wrong if you attend tutorial and you do not pass. That can be the only way it would be wrong. Right? Do you agree with that? Okay. Now, can you look at some other combination of this to get this statement, this truth table, truth value? What I do with P or Q, or how I change this connective, that I get still the same table. So what I mean is, I want to get the same table, but some alternative means. What operations are you going to use on these two that I get exactly the same table? So you can change them around. You can put something like or and or whatever symbols between them, and you get the same table. Yes?
What's the and for other form?
It's closer to and. P and Q. So true, true, true. True, false, false. False, true. It has to be false, but here it is true. It's not and.
It was not in front of classifications.
Yes, you can. For what? Which one?
The thing you start off with.
So let's say I put not P. Not P will convert this true into false, false, true, true, right? Now what operation I do now? False, true, that it becomes true, false, 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 true, 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 false, true. So this is not P or Q. just think. This proposition or that proposition, so you have F or T is T, F or F is F, T or T is T, T or F is T. So this implies, can be, this P implies Q can be rewritten as not P or Q. There is a reason I'm writing in this way. At a later stage, next week, we will be solving equations. Just like, in school you have solved 2x squared plus 5x plus 8x plus 9y multiplied by some 10 to the power 5, something like that. In school you have solved these kind of equations, right? You said you simplified them, you put them equals to some smaller, some condensed values, equations. We're going to solve similar kind of equations here. So we have to know and, or, if then, if and only if tables. Okay? So thinking in this way of writing alternative means is helpful. It's very helpful. And that can only be mastered while in the practice. Nothing more. Right. Let's move on. So we were here. Suppose your lecturer claims we've done all this discussion, so I'm skipping it. So then we're still going if then connected. So you would have T, F, T, T, this table, and an alternative way, which we're going to do next week. I just gave you a hint of that what's going to happen at that time. So now, based on this, we can assign truth values to some weird sentences. If the sky is blue, then cows have 4 legs. Both propositions which are connected by if then has nothing to do with each other. But we are not checking them. All right? We just want to make these kind of tables and draw conclusions from those tables. Similarly, are the following proposition true or false? If the sky is yellow, then cows have 6 legs.
False.
We haven't seen cows 6 legs.
I haven't seen a yellow sky either.
So, how do we know?
Well, what about when the sun sets? Before it sets.
Some
sky is yellow.
Come on, that's
Maybe
not
it's
yellow.
Maybe when the sky goes yellow and you're up to
No, look, what I'm saying is,
Is it right here?
the thing I want to explain there is, irrespective, if your claim is not true, whatever the conclusion, your statement is not wrong. If Sue has not attended tutorial, whatever the outcome, your claim is not wrong. That's the point we are making. So this is a true statement.
Yeah, that's what I'm saying.
You was right.
I was saying that.
Yes, okay, yeah, I know. No, okay, I didn't point out that you're wrong, did I? I never said you're wrong. I hardly ever say people are wrong. It's all relative here, these statements. There are different interpretations you can have. If the sky is blue, then cows have 6 legs. You can draw that conclusion as well. Anyway, this is not the point that we draw conclusions on it. The point is how you make these tables, how you connect them using these atomic propositions and symbolic logic. Then the connective if and only if. This can only be true if both the propositions are true. So you're implying one thing to another. Okay? Right. Okay, so let's look at some example. So this can only be true if both of them are true. So the table would be, this is true and that is true, so it is true. True, false, so it has to be false. False, true, it has to be false. But these both are the same, right? So it has to be true. This is if and only if statement. Equivalent statement, so that means equal. So true and true are equal. So that's why it is true. F and F are equal, so that's why it is true. Right. So this is the example is that the proposition Bendigo is in China if and only if apples are blue is true.
Chinatown.
Right.
Let's go to Chinatown. That's when the venue is. Here we go to Chinatown. The venue stores.
How many of you have been to China? Anyone been to China? Really? Okay. That's 1/4 of the world. More than what? No. Hardly anything.
How long's the flight to get over there?
Depends which airline you choose. If you want to go by Emirates, first it will take you to Dubai, 14 hours from Melbourne, which is again another thing, and then from Dubai to whichever part of China you want to go, and it depends. Sometimes you have to take lots of domestic flights there. Okay, I'm just saying that you might have, if you have gone there, you might have seen Bendigo over there. So. What?
Yeah, 12-hour flight from Melbourne to Beijing.
Yeah, but Emirates, that's what I meant.
Oh, that, I'm saying direct.
Oh, yeah, there are direct flights, of course. If you go by China Southern or Eastern China Airlines and all that, of course you can get direct flight.
We can all go to China every Easter.
Well, my question is, can you find Bendigo over there? That was my question. Bendigo is in China if and only if apples are blue is true statement, right? Because both propositions are false. Yeah, it falls in this category. Yeah, this one. Have you ever seen blue apple? The natural color. I mean, yeah, we have not colored it. No, I never saw it. Anyway. However, I have seen Toronto in Australia. I can't write that, you know. And I have seen lots of other cities with similar names. Oh my God.
Richmond,
What?
Richmond's from here and over in the States somewhere.
Is it?
Yeah. Same as Melbourne, Melbourne, they call it.
Sydney.
Sydney.
Yeah. Okay. Examples of developing a truth table. Let's look at that. In the next lecture, we'll illustrate and practice developing a truth table from expression, and after that, we will start solving equations like that, but written in propositional logic form. So here is a preview of what we will be doing. Develop a truth table for this. Well, let's do that, should we? Maybe. How about you give it a go? There is no judgment you're right or wrong. It is just intuitively you want to build. You want to develop a table like this. Since I have not given you example or anything, I will not test you on it. So even if you are wrong, you should not worry about anything. So the first thing is to try. Can you develop a table like that for this? And then I would solve and see if you have the right answer or not. So your basic logic table would stay the same, P and Q, and the rest you have to build. So, well, I've split the table into smaller and smaller parts, and then I'll put them together. Okay, now I'm looking at Q or this statement. So true or true is true, false or false is false, true or true is true, and false or true is true. So in the end, my table is this. Yeah, I might be wrong. You just have to test yourself. Well, let me write it down here. If you have not, I want to explain my thinking process. My thinking process is you want to find out what is Q or not Q and P, right? Okay. So what I want to do here in all of this, I want to find out values for this one, and for that, I need to know what is not Q is. So I first put not Q here. So not Q becomes true, it's true, so it becomes false. This false becomes true, that false, and that is true, right? Okay. Now, not Q I know, then I want to determine not Q and P. So not Q and P. Now, and statement, if one is true and the other is false, it has to be false. True and true is true. False and false is false. And false and true is false. Right? And then what we want after that, once you have that, it says not on the end of it. So we have to calculate what this entire value would be. So not of not Q and P, so I have to put not there. So not means this entire values would flip, so true, false, true, true, right? So I have calculated this part. Now I have to do the or sign between Q or whatever I have here. So Q or, if this is my value A, whatever that thing is, Q or this. So Q or that. So that would be true or true is true. False or false is false. True or true is true. And false or true is true. So this is your for all that. You got the same? Have you? Good. Now, you see that making this table is although easy, but long process. Do you see this table is equals to some other values in this all of these columns? Is this equals to any other column? Yeah, exactly. Anything else? Yeah, nothing else. So this equation is equals to not Q and P, which would be equals to, we will do that later. Don't be intimidated with this. This would be equals to not Q or not P, which is equals to Q or not P. So this value is the simplified version of all of this. Okay, we will do that later, but for the time being, just we have to learn how to draw, how to make these tables, and then we find out how we can simplify them. Okay, step by step. Okay, so that's what we have there. So we draw step by step. Information is given. You can check them. I've tried to explain everything step by step, and in the end we draw the table, which is TFTT. This final value was we were interested in. Yeah. However, can be further simplified as I explained. Whatever we are doing, that's not the end of the world. That's the point I'm making. There is always something new coming up. There's always space to create more, to improvise, to make it better. Yeah? Okay. Fantastic. Any questions? Come on, you should have some questions. No. Academic, non-academic? What did you say? Fried?
Yeah.
What did you do?
Just been listening to maths.
Too much maths. Are you only done 2 lectures today?
4.
Maths, he said.
Yeah, we went pretty much programming is the same thing
Ah,
at this point.
yeah, it is always pretty much the same thing. You would use, if you're good at maths, you'd be good at programming in the end. It goes there a lot. Anyway, if you don't have any more questions, have a good rest of the week, and I'll see you guys next week. Remember, any questions, just send me an email anytime. All right, guys.
Having done long division since I was about Clayton Jones' year 8 maths class. He was doing oh, right. Yeah, that's cool. Going multiplying ways to different ways and then off to go non-thomas classes. Always last one, so.